This is section 8.2, and it's about combinations. And so I pulled a really good example from the text to kind of get us in a right frame of mind to see the difference about combinations or between combinations and permutations. So in the previous section, we saw that if a teacher wanted to arrange 3 out of 5 different books on his desk, that is 60 permutations of 5 taken 3 at a time. So 5 NPR 3. So if you have 5 books and you take them 3 at a time, there were 60 different ways that the teacher could arrange them. Now, what if the teacher doesn't wish to arrange the books on your desk, but wants to choose, without regard to order, any 3 of the 5 books for a book sale to raise money? How many ways could that be done? And sometimes at the first we say, oh, that'd be 60 again. But it's incorrect. The number 60 counts all possible arrangements of 3 books, because that would be a different arrangement like on a desk. But if you're just choosing books to give to a sale, these that are the arrangements, you're still getting a mystery, a biography, a textbook, whether they're in this order, or this order, or this or this. So these 6 arrangements lead to the same set of 3 books being given to the book sale. So it's only one subset of 3 books, but it's 6 different arrangements. A subset of items listed without regard to order is called a combination. And so that's C, 5 taken 3 at a time. And since they're subsets, combinations don't require order. Order does not matter. It matters in permutations. So if we do that, the actual formula, I'm going to show you in just a second, but we get 10. There's 10 ways that the teacher could choose 3 books for the book sale. So if we look down here a little bit, the actual formula that's going on is n factorial over n minus r factorial times r factorial. You're not going to have to do that by hand. You're going to use your calculator for most of that. So sometimes we'll see it written like this: 8 things taken 3 at a time. We could do it by hand and we could get 56, even using the factorial on your calculator. You could do that. Or we can simply do it with calculator, go to math, over to probability, find NCR. And so if we did that one, just to clarify here, so we've got our calculator and we're going to go to math, over to probability. Whoops, I went one too far. Choose number 3, NCR. Oh, I had answer in there. Let me see if we can make this. Oh, I've got it in the old format. Okay, if we do it in the old format, we're going to type 13. If you have an older calculator, then you're going to go to math, over to probability, choose number 3, and then put in your 6, and then enter, and we get the 1716. If you have the new one, let's see if I can get that just so that we see both. All right, so we would go to math, over to probability, oops, and choose number 3, and we just get the boxes. So it's 13 goes in the first box, and we tab over, put 6 in the second box, and enter, and we get that. So regardless of which calculator you have, you can make this happen with your calculator. Okay, so let's move on. We went too far. All right, so here's an example. Economics Club has 31 members. How many ways can a committee of 4 be made? Does it matter the order of the members in the committee? It doesn't. So 31 taken 4 at a time. So we would just do that on our calculator, and the same thing, math, over to probability. I keep going too many times. and we put 31, tab over, and put 4, and we get 31,465. In how many ways can a committee of at least one, at most 3, be made? So it's kind of the counting principle. So you'll take 31 things taken 1 at a time, taken 2 at a time, taken 3 at a time, and then add those items together to get 4991. So use the counting principle plus the combinations. All right, musical chairs. 12 children sit in 11 chairs. In how many ways can this happen if we count rearrangements of children as different outcomes? So is this a permutation or a combination? Well, since we said rearrangements count as different outcomes, that means order matters. So this is a permutation. It is 12 children taken 11 at a time. And so if we do that, look at the number that we get when we do that. Very large number. All right, a club with 9 males and 11 female members need a committee of 5 people. How many committees can be selected that have at least 4 women? All right, so let's think about it. We could have, for 5 people, we could have 4 women and 1 man, or 5 women and 0 men. All right, so we would have one combination that is the 11 females and we want to get 4, and 9 males and we want to have 1, and we multiply those together, we get 2970. Let's do that on our calculator. So I put that up there to show you you can do it like this. You could do it in parentheses and multiplying, but I did a combination of 11, 4, and I got 330, and then I just hit my multiplication sign, and then I hit probability math, math probability, and went to the same thing, and I just said take that answer, multiply it by 9C1, which was here, and I got the 2970. So, and then this one is 11 taken 5 at a time, and then 9 and 0. I added those two together and got a total of 32 ways that committee, how many committees can be selected. Okay. A committee with no more than 2 men. So you either would have 0 men, 1 man, or 2. And then that would leave, because you have 5 total, 5 women, 4 women, 3 women, we do it the same way. 9 taken 0, taken 1, taken 2, and 11 taken those. Multiplying, you get these numbers, add them together, and you get the 9,372. All right, next example. We have 7 rotten apples that are in a crate that has 26 total apples. How many samples of 3 apples can be drawn? Okay. So this is just saying how many groups of 3 can you get? Well, you have 26 total, taken 3 at a time, so that would give you 2,600. Okay. How many samples of 3 apples that are all rotten? Well, there's only 7 that are rotten. So in how many ways could we take 7 apples 3 at a time so that we were getting rotten every time? And that would be 35. How many samples of 3 apples where you would get 2 good ones and 1 rotten? All right, so if we want 1 rotten, there were 7, and we're going to choose 1. That leaves us 19 that are good, and we want 2 of those. So 7 taken 1 at a time times 19 taken 2 at a time, and we get 1197. How many 13-card bridge hands could be in an ordinary deck? Okay, so 13 is the number in the bridge hand that we want. There's 52 cards total. So 52 taken 13 at a time, we have a huge number. All right. So that's an overview for combinations. Let's go look at our problems. All right, so we start out with some basic just calculator questions. Evaluate combination of 11 things taken 4 at a time. And this is on the newer calculator, but remember, if you're going to have the older one, you would type 11 first, then math, probability, NCR, and then the 4. If you're doing it on this newer style, you can just do math, probability, NCR, and you will get that with the little boxes. So it just depends on your calculator. Evaluate the combination of 35 things taken 21 at a time, and it says use scientific notation, round to 3 decimal places. So if you're doing it in the calculator, 35 taken 21 at a time, and then we get this number, and we want to round to 3 decimal places. So that means we bring this all the way here for our decimal point, 2.319. There's a 9 there, so we're going to round to 0 there. So that's where we get the 2.320. And how many places is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10 to the 9th. And you may have to use, there's a multiplication symbol in the math palette, it says. You can also use the one, I think, on your computer. But that's what you're doing with that one, turning this large number into scientific notation. In how many ways can a hand of 7 diamonds be chosen from an ordinary deck? So there's 13 diamonds total, so we're actually doing a combination of 13 taken 7 at a time, calculator 1716. All right, 7 cards are marked with the numbers 1 through 7 and then shuffled, and 2 cards are drawn. A part, how many different 2-card combinations are possible? Well, that's simply 7 taken 2 at a time, and you would get 21. How many cards, 3 or greater? Well, how many things are beyond 3? 1, 2, 3, 4, 5. So there's 5 cards, and you're drawing 2-card hands. I didn't write that down there, but 2. So 5 taken 2 at a time would equal 10. So when we did this, we found out how many cards there were that were 3 or greater, and that was 5 taken 2 at a time. That would be 10. Well, there were 21 possible 2-card hands total, and this is how many are 3 or greater. So if we do 21 minus this 10, we get the number less than 3. Okay, we kind of worked backwards on that one. How many different committees can be formed from 10 teachers and 41 students if the committee consists of 2 teachers and 3 students? So in how many ways can the committee of 5 be selected? So we need 2 teachers, so that's 10 taken 2 at a time, and then 41 taken 3 at a time. And we're going to multiply those together, and when we do, we get 479, 700. So choosing a teacher's one event and choosing a student's another, so we're using that counting principle where we have 2 things going on. Game of musical chairs. 9 children will sit in 8 chairs arranged in a row. 1 will be left out. In how many ways can this happen if, again, like our example, we count rearrangements as different outcomes? That means order matters. So that would be a permutation. So now we have 9 children taken 8 at a time in a permutation, and we get this number as our answer. Marbles are being drawn without replacement from a bag containing 10 marbles. First, decide whether it involves permutation or combination. So, does order matter? No. So, how many samples of 4 marbles can be drawn? We have 10 taken 4 at a time, 210. How many samples of 2? 10 taking 2 at a time, 45. If the bag contains 4 red, 3 green, and 3 black, how many samples of 2 marbles can be drawn in which both marbles are black? So we say, okay, we're going to have 3 to start with. 3 taken 2 at a time would be 3. All right. An urn contains 9 white balls and 3 red balls. 3 balls are going to be selected. In how many ways can the 3 balls be drawn from the total of 13? And there's 3 questions that they ask. If 2 balls are white and 1 is red. All right, so the 9 white taken 2 at a time and 4 red taken 1 at a time, and then we multiply them, we get 144. Remember, order doesn't matter, so this is a combination. B, the 3 balls can be drawn if 3 are white, if all 3 are white. So we had 9 white, taken 3 at a time, we get 84. And then if all 3 are red, remember we had 4 red total, so 4 balls taken 3 at a time would be 4. Okay. Company sells regular hamburgers as well as a larger burger. Either type can include cheese, relish, lettuce, tomato, mustard, or ketchup. How many different hamburgers can be ordered with exactly 5 extras? Order doesn't matter. Doesn't matter the order of the extras. So this is a combination. All right. How many different hamburgers that can be made using exactly 5 of the extras? There's 6 extras total. 1, 2, 3, 4, 5, 6. So 6 taken 5 at a time. So, all right, so our first part says there are how many different hamburgers that can be made using exactly 5 of the extras. We have 6 extras and we want to take 5 at a time. The 2 comes because we have 2 different sizes that could be happening. We've got either a regular hamburger or a larger burger. So because there's 2, we do the combination of 6 taken 5 at a time, and then we multiply it by 2 to get 12. B, there are how many different regular burgers. So now we've eliminated the larger one. And so now we just have the 6 taken 5 at a time. That's 6 burgers. And C, we're still with just regular, so we don't have the 2 now, again, with 4 extras. So it's 6 taken 4 at a time. So because it said at least 4, well, we could have 4 ingredients extra, we could have 5, we could have 6. So that's 3 combinations, and we'll use our counting principle and add them. So 6 taken 4 at a time is 15. 6 taken 5 at a time is 6, and 6 taken 6 at a time is 1. Add those together and we get 22. So I think that should get you through the problems on 8.2.